Hello, everybody, and welcome to the Climate Report. I'm your host, Noah Boss, and today's episode will be on the cryosphere and oceans. The first thing I want to do is zoom out and take a look at where the extra heat from global warming is being distributed in the Earth's system. The global oceans absorb the vast majority of this heat, taking up roughly 89% of the total extra energy being absorbed. The land comes in at second at 5%, then the cryosphere at 4%, and finally the atmosphere at 2%. Looking at this distribution of heat, it is no wonder many of the greatest concerns around climate change involve changes to our oceans, though it is important not to underestimate the amount of heat being absorbed in the land, ice, and atmosphere. While the amount of heat seems comparably insignificant, the relatively small heat capacity of the land, ice, and atmosphere as compared to the global oceans results in this heat having a profound impact on these systems. To put this into perspective, water is roughly 800 times more dense than air at sea level, and has 4 times the heat capacity for a given mass. This means that it takes more than 3,000 times as much energy to heat a volume of water than an equivalent volume of air. Now let's zoom in on the heat that is being absorbed from melting ice. This graph shows heat uptake in zettajoules of the various major components of the cryosphere. The axis on the right shows how this heat uptake translates into mass loss, which is measured in teratons. In case you aren't familiar, a zettajoule is 1 sextillion joules, and a teraton is 1 trillion tons. The global mass loss of ice from 1979 to 2020 in this analysis is estimated to be about 38 teratons, which resulted from an energy absorption of 13 zettajoules, though there is uncertainty in these numbers, which is represented in the shaded area. As of 2020, the Antarctic ice sheet contributed the most to cumulative mass loss, with glaciers second, Arctic sea ice third, the Greenland ice sheet fourth, and lastly, Antarctic sea ice. If you watched my last video, you know that Antarctic sea ice has suffered significant loss since 2020, so an updated figure would likely be slightly different. It should be noted that sea ice mass loss, shown here, does not contribute to sea level rise, as the ice is already displacing its mass as it floats in the ocean, though there are a myriad of ways in which sea ice is important to the stability of our current climate conditions. Now I will briefly take a closer look at mass loss trends for land-based ice, which directly contributes to sea level rise. This graph shows the cumulative glacier mass loss globally from 1976 to 2023. The total loss shown here is 8,226 gigatons, which is equivalent to 8.2 teratons. This amount of mass loss would roughly contribute 23 millimeters to global sea levels. This graph clearly shows the rate of mass loss is increasing with time. This graph shows the cumulative mass loss and resultant sea level rise from the Greenland ice sheet. This dataset indicates a 5.5 teraton loss in the Greenland ice sheet's mass between the 1970s and 2023, and a resulting 15 millimeter contribution to sea level rise. Now let's take a look at the Antarctic ice sheet. Overall, the Antarctic ice sheet lost about 5 teratons from 1980 to 2023, which contributed nearly 14 millimeters to sea level rise. Crucially, this figure breaks down the contribution of mass loss by region. The West Antarctic ice sheet is by far the greatest contributor to mass loss, and despite East Antarctica containing far more ice mass, it has remained nearly stable in recent decades. The West Antarctic ice sheet is home to the Thwaites Glacier, which is often referred to as the Doomsday Glacier by the media and even many scientists discussing the topic. I plan on making a future video that specifically focuses on the Thwaites Glacier, but for now, the important takeaway is that the West Antarctic ice sheet is particularly vulnerable because of many of its glaciers having grounding lines below sea level, allowing warmer ocean water to melt the ice from underneath. As ocean temperatures rise, this process destabilizes the ice sheet and accelerates its flow towards the coast. This graphic provides a visualization of where the mass loss is occurring for both the Greenland and Antarctic ice sheet. The greatest mass losses occur in lower elevations near the coast, whereas many higher elevations are actually experiencing a net gain in mass. This is because higher elevations experience much less melt due to lower temperatures, and the amount of snow received at these locations exceed the amount of mass lost from melt. In lower elevations, warming temperatures are resulting in an increasingly net negative mass balance due to the increase in melt and decrease in the proportion of precipitation that falls as snow. In addition to increased melt from a warmer atmosphere, marine terminating glaciers are also experiencing accelerated melting from higher ocean heat content. Permafrost is another important component of the cryosphere. Permafrost is defined as any ground that remains frozen for at least 2 years straight, though much of the permafrost deep underground and in high latitudes have been frozen for much longer. The oldest permafrost discovered was in a location in eastern Siberia, 50 meters underground, which was frozen for the past 650,000 years. Permafrost is important to our current climate regime because it stores organic matter, which can be consumed by microbes once thawed and then released into the atmosphere as carbon dioxide or methane. The 2024 Arctic Report Card, released by NOAA, found that Arctic tundra has recently switched from a carbon sink to a carbon source due to permafrost thaw and wildfire activity. The Arctic tundra has been a carbon sink for thousands of years, so this represents a new and growing source of greenhouse gases that act as a feedback to climate warming. The report also indicated that the boreal region is still acting as a carbon sink, with increasing growth rates of boreal vegetation offsetting increases in positive fluxes from permafrost thaw and wildfire activity. The regional balance of carbon can be seen in this image, with red indicating a net source of carbon and blue indicating a net sink. This data from NOAA shows the change in global mean sea level from 1880 to 2024. Throughout this period, global sea level has increased 21 to 24 centimeters, or 8 to 9 inches. The rate of sea level rise is accelerating, with recent years approaching 5 millimeters per year, while the 20th century average was closer to 1.5 millimeters per year. It is important to note that the land ice loss is not the only major contributor to sea level rise. The thermal expansion of ocean water from increasing ocean heat content as a result of global warming is a major contributor to sea level rise. While sea level is increasing globally, this is not occurring uniformly across the planet. Some regions are experiencing faster rates of sea level rise than others, as can be seen in this graph. Some of the major factors that influence local sea level rise include the uneven heating and thus thermal expansion of the ocean, melting ice sheets reducing their gravitational pull on surrounding water, changes in ocean currents, and regional land subsidence or uplift. Another alarming consequence of our carbon dioxide emissions is the resultant ocean acidification. Here we see the change in ocean pH over time. As atmospheric CO2 levels rise, more carbon dioxide dissolves into seawater, forming carbonic acid and lowering the ocean's pH. This trend is concerning because even small decreases in pH can disrupt marine ecosystems, particularly organisms like coral, shellfish, and plankton that rely on calcium carbonate to build their shells and skeletons. Similar to sea level rise, ocean acidification is not felt uniformly across the planet. Notably, polar regions are experiencing faster rates of acidification due to colder waters absorbing CO2 more readily. Climate change is also causing our oceans to become increasingly stratified. Ocean stratification refers to the layering of water masses with different densities, which is primarily determined by variations in temperature and salinity. Mixing between these layers is crucial for distributing oxygen, nutrients, and heat throughout the ocean. However, climate change is disrupting this process. As surface waters warm due to rising global temperatures, their density decreases, making them more buoyant. This creates a stronger contrast with the cooler, denser waters below, particularly across a boundary layer known as the pycnocline, the zone where water density changes most rapidly with depth. The strengthening of this pycnocline acts like a barrier, reducing vertical mixing and limiting the exchange of heat, oxygen, and nutrients between layers. As a result, surface waters become increasingly nutrient poor, and deeper waters become increasingly oxygen depleted, impacting ocean productivity and biodiversity. This graph illustrates changes in ocean stratification within the upper 2,000 meters over time, highlighting a clear upward trend. As you can see, stratification has intensified significantly in recent decades, with a sharp spike in 2023 that quite literally goes off the chart. This unprecedented increase is primarily due to rising surface temperatures, which amplify density differences between layers. The strong El Niño event in 2023 further contributed to this spike. While the long-term trend is being driven by climate change, El Niño events are associated with short-term spikes in ocean stratification. The two previous spikes are associated with the 1997 and 2015 Super El Niños, which are among the strongest El Niño events on record. The recent El Niño in 2023 was not as intense as these two events, supporting the fact that the long-term trend played a significant role in this new record for ocean stratification. In addition to stratification of surface waters, Climate change is having an impact on the global meridional overturning circulation. Recent research has indicated that we may be approaching a tipping point in global ocean circulation sooner than was once thought, with the possibility of this occurring sometime this century. The impact on the climate system this would have would be severe, because this circulation system is responsible for a significant amount of heat being transported from the southern hemisphere to the northern hemisphere and from the tropics to the poles. Because of the complexity of this topic, as well as its significance on the global climate system and human society, I'll be creating an entire video dedicated to this subject soon, so make sure to subscribe if you don't want to miss it. That wraps up today's episode. If you enjoyed this video, don't forget to like, share, and subscribe to stay updated with future content. As always, I'd love to hear your thoughts and questions, so feel free to drop a comment below. Thanks for watching.